So skewness of distributions, in order to talk about how a distribution is skewed, we would first need to talk about how a distribution is normal. So a normal looking distribution, the word we would use is symmetric. And symmetric distributions, the word symmetric is like roughly even on each side. So if I drew you a symmetric like distribution that was a smooth curve, it would be something like that bell-shaped curve or the normal curve that you're used to seeing. If you can see the bars, we're talking about a histogram still. And the histograms, as you get more and more bars in there, when they tightly pack them and the bars get smaller and smaller, eventually they become smooth like this. If we were to say you had infinitely many bars, suddenly they become a nice smooth curve, which is what calculus really is all about. But don't worry, you don't have to know calculus in order to be able to do stats 13. But when we're talking about symmetric, we mean that roughly there's the same amount of data over here as there is over here. So see, for 4 and 5, it looks like the box only goes up 1. And the same thing for 9 and 10, it looks like the box only goes up 1. And then for 6, it looks like the box goes up 3. And over here at 8, it looks like the box also goes up 3. So it's roughly equal on each side. And then, you know, we could like cut it down the middle and say this side is equivalent to this side. When that happens, the mean and the median are exactly the same. So you'll see how I have labeled on here, the mean is 7 and the median is also 7. When we have a symmetric distribution, they're the same number. But usually distributions are not perfectly symmetric. Normally, they have a little bit of skewness to them. When they say things are roughly symmetric, that's usually a good sign that we can use a lot of our statistical tools. When we have a lot of skewness happening, it means things get shifted either off to the left or off to the right. And the shifting makes things not quite so clean when we're doing like our evaluations of things. So when we're looking at this second set of histograms down here, if I wanted to know where's the exact middle of this data, remember that's what the median would be, the exact middle of the data isn't going to be right cleanly down the middle at 8, because we've got kind of more of our data stacked in these bigger bars. And so what's happening is the mean and the median are getting skewed, is the word that we use. And we look for where the longer tail is on our data. And when we say a tail, that's where it kind of lowers down. So we have a tiny tail over here, but we have a longer tail over here. And so we would say, if I were to draw like a smooth curve over this, that the tail is off to the right-hand side. This is called a right-tailed or a right-skewed distribution because the tail is off to the right. So I'm going to draw a smoother looking curve instead of the bars here, and I'm going to make the tail kind of exaggerated. There's my tail. The tail is off to the right, so this is called right-tailed. Or another way to say that is right-skewed. And what happens when we have a right-tailed or a right-skewed distribution is that the mean actually ends up being a bigger number than the median. And this kind of goes back to those of you who were here when I was talking about Bill Gates's grandson throwing off our data because he's making a bunch more money than the average UC Davis student. So in this case, most of our data is kind of hanging out over with these smaller numbers, 6, 7, and 8. But we've got a few data points that are over here at 9 and 10. And what that's doing is it's skewing our data and it's pulling that mean to the bigger numbers over here. So whenever you've got the right tail, your mean is going to be further off to the right. Now, we could actually take all these numbers and add them up if you wanted to, and we could go find that the mean is 7.7 and the median 7.5, but you probably believe me. When we have right-tailed or right-skewed distributions, generally what we want to remember is that the mean is greater than the median. So I'm going to write that symbol down here, that the mean is greater than the median. Okay, if I go back up to our symmetric distribution, we said that the mean was equal to the median. And so if we look at this last distribution down here, we kind of have a reversal, and the taller blocks are over here on the bigger numbers, which you can't see because I didn't push the paper up all the way. There we go. There's my bigger numbers. So we've got more amount of our data sort of clustered at that 6 and 7, but the tail, the longer tail, is now off to the left. So we would say that this one is left-tailed or left-skewed. And so that means that if I were to try and find the exact center of the data again, the exact center of the data is going to be like somewhere here, but the mean is going to be before it because these smaller numbers are pulling that mean over to the left-hand side. So you can see by these numbers, the mean this time is smaller than the median. So I'm going to write that in symbols. The mean is less than the median. So if you're like, how am I going to remember that, Jen? Skewness pulls the mean toward the tail. The skewness pulls the mean toward the tail. So in this case, the tail was over on the left, so it's pulling the mean over to the left. And so since the mean is over to the left, it's smaller than the median. And then in this case, the mean, the bigger number was the mean. And so the tail was over here. It's pulling the mean toward that tail. And now that mean is bigger than the median. So the skewness always pulls the mean toward its tail. How many questions are going to come up like this on your exams and stuff? Not a huge number of them, but from time to time, what they'll do is they'll give you some pictures of things and they'll say, describe the distribution. And if you're staring at a distribution that has roughly the same amount of data on this side as on this side, you'll want to call it symmetric. That's the magic word you'll want to use. But if you see a distribution where more of the data is sort of grouped up over here and there's a tail off to the right-hand side, you'd say that's right skewed. And if more of your data is grouped up over here and then you have a tail off to the left-hand side, you'll say that's left skewed. So we use it as just a way of kind of generally talking about the shapes of things. We don't usually have a whole lot of questions where we're like, okay, so does that mean the mean is going to be bigger than the median? There's not a whole lot of that. But occasionally those types of questions will pop up. So it's good to be able to tell the difference between where the mean and the median are going to go. But where I see these questions come up the most are more, can you describe the shape of the distribution? And so we would say symmetric, right skewed, left skewed. Comes up a lot. Questions on that? The next topic's like one of the coolest topics. So I'm like so excited to get there. But please ask a question. I won't rush it. Oh, excellent question. Could we tell off of a box plot if something is skewed? That like deserves a separate piece of paper. So let me get a separate piece of paper. That was a very good question. I was talking to people the other day about how I wish I had learned to ask better questions when I was a student, because I was one of those people in class where I had no idea what was happening while class was going on. Anybody else feel like that? Like during class time, you're like, what the heck? And then like later when I do problems on my own or whatever, I'm like, oh, okay. But during class time, they're like, do you have any questions? And I'm like, I don't even know what just happened. Literally, I can't ask you a question right now. Hard. Okay, so the question was, hey, Jen, if we've got a box plot instead of those cool histograms, or instead of the smooth distribution that I drew. So we were doing box plots before. And so we might have something like this, and this, and let's say, let's put some cute numbers here. So I'm going to say this is 2 right here, and I'll say this is 4 right here, and I'll say this is 6, and I'll say this is 8, and I'll say this is 10. Okay, so if we had like a number line below it. Okay. Staring at this particular box plot, my whiskers have the same length. And how I've drawn this so far, I haven't gone and put the median in yet, but let me put the median in there. There's my median, okay? Staring at this particular box plot, I would say this is a symmetric distribution. In the same way that we said that this first histogram was symmetric, because the middle part, we have like the same thing happening on both sides. Like from here to here was 2, from here to here was 2, from here to here was 2, from here to here was 2. It's like the same, it's all nice. Symmetric means that when you cut it in half, you've got essentially the same thing on each side of your half mark. So this would still be symmetric, but let me draw you something that's not symmetric. Okay, already not symmetric because I got a crazy long whisker over there, right? And then I could throw that even more by putting my median bar right there. So it's not even in the middle of the box, right? This whisker is acting like the tail on our distribution here. We got a real long tail over on this side. This whisker is acting like a really long tail. So I would say that this thing, because the tail is off to the left-hand side, I would say that this was left skewed. And you could do the same thing and make a right skewed one if we make a longer tail the other direction too. I feel like I have to put it further back over here, maybe. Okay. Question. You can't tell where the mean is on a box plot. We can always tell where the median is on a box plot. Good point. Good point. So for you to be able to tell me for sure where the mean is located, we don't put that on a box plot. But the line that goes through the box, that's always going to be the median on a box plot. This one, the median was even further over on the box. This could still be kind of more in the center here, and that's okay. Having the longer tail is still going to create the skewing situation. So I would still say this was right skewed, even though this one was kind of more centered in the box. But as we start to draw ones, I'm going to draw you kind of an ambiguous one, and you'd be like, I don't know how I would describe it. And I'd say, you probably wouldn't describe it this way. So if I drew you something like this, and Like, that's not symmetric. And there is a little bit of a pull happening here, but there's nothing like too crazy happening. I would still say that this was probably like roughly symmetric, or I would say slightly left skewed, but I wouldn't go crazy. I wouldn't be like, this is a crazy left skewed distribution. Whereas that one, I'm like, oh, that's definitely a left skewed distribution. So when we're talking about things in stats, how we decide when we're going to describe something as symmetric or not symmetric, it's sort of like it's not an exact science. Like in some cases, how you're coming up with that is sort of based on like you're looking at a bunch of different plots and you're like, well, all of these kind of sort of look pretty normal, pretty symmetric. And then these ones over here definitely look left skewed. And then you kind of have these ambiguous ones where you kind of have to just like decide where you feel like you should put it. So that can be really frustrating in statistics because people are like, I'm used to in math, there's like a definite right answer. And in stats, there's a lot of, it depends. And so in this case, I'd be like, I'd maybe say slightly left skewed. But it's not like the one up here where I was like, definitely left skewed. That's a great question. Yes, we can tell from box plots. But also another great point, what I can't tell you is where is the mean located just by staring at a box plot. It doesn't tell us that. But the line does tell us where the median is located. All right, before I forget, let me pass around the sign-in sheet. So remember, everyone's allowed to just audit the class if you would like. If you're actually enrolled in the class, you have to come to 15 out of the 20 class sessions. This is class session number 4. So what I'm going to do probably next week is send out some emails to people who've missed a bunch of class sessions, and I'll say, I don't want you to be at risk of getting a not pass in the class. Totally drop it, and it won't hurt anything. You can still come, and I'll add you back to Canvas and all the other things. So if you're worried about your attendance, just go ahead and drop it from Schedule Builder, and then just keep coming, and I'll add you back to Canvas. You just have to let me know, because when it drops you, it automatically takes you out of the Canvas, but Jen can put you back in. So not a big deal. If you want the one workload unit, though, you're going to aim to come to 15 of these at least. I mean, obviously come to all of them, but you want to try and get 15 out of the 20. Questions on that? Beautiful. Okay. All right. I'm a total dork, so I'm excited about this next topic because it's like a thing you hear about a lot in statistics, and lots of people don't understand how it works. Measures of the spreads of the data. Did you guys talk about standard deviation? Okay. Spread of the data. So remember a few days ago, I talked about measures of central tendency, and I said the word average is kind of problematic in statistics because when we say average, we could mean the mean or the median or the mode. Measures of central tendency are talking about things that are like where things are grouped toward the center of our distribution. Spread is how far apart are all of our numbers. So like, if I was talking about scores in a particular statistics class maybe, and so everybody took a quiz, and you got a 9, and you got a 9, and you got a 9, and you got a 9.5, and you got a 9, and you got a 9, and you got a 9.5, and you got a 9 and a 9 and a 9.5 and a 9 and a 9 and a 9.5. I'd say there's not a lot of spread happening because y'all scored really close together. But there could be another statistics section, maybe it's like the 7:30 a.m. section, and someone got like a 1 and a 2, and there were a bunch of zeros because people slept in. But then there were a 10 and a 10 and a 10 and a 9 and a 1 and a 0. The spread is huge in that class. So spread is how far apart are they roughly from each other? Are they really grouped closely together, or are your scores kind of far apart? And there's different ways that we can talk about the spread. The 3 ways we usually talk about the spread are the range, the variance, and the standard deviation. So the most basic way we talk about the spread It's just to talk about the biggest number minus the smallest number. So if I've got that one section and someone got a 10 and someone got a 0, the range is 10. We'd say 10 minus 0. So that's the biggest. And then in the class where 9.5 is the highest score and 9 was the lowest score, the range is 0.5. Super tiny range, right? And that can be really, really helpful, but it's not going to tell us everything. Here's why. So I've got an example here. Data set number 1, these are scores on a test. A 90, a 90, a 90, a 98, and a 98. So if I did the range, we would take the biggest value, the 98, and we'd subtract the smallest value, the 90. What would my range be? 8, okay? Now I have another data set. 1, 2, 6, 8, 9, and 5. These are way worse scores. Imagine it's the same test. Okay, but the biggest number was a 9, and the smallest number was a 1. What was the range? Same range. So that didn't tell us enough information. Like, it told us how far apart the highest and lowest score are, but it didn't really tell us anything about the scores themselves, right? And so we need something else that's also going to kind of talk about the scores themselves. And that's where variance and standard deviation come in. So we're going to introduce 2 other measures of, we say variation is how much your data is different from each other. The variance and the standard deviation are actually really related to each other. If you can calculate the variance, you can calculate the standard deviation, because all the standard deviation is when you take the square root of the variance number. So once you got the variance, you just either hit the square root button on your calculator, or if the number's nice, like 100, then you can do it in your head. So standard deviation is just the square root of the variance. Variance is a thing that lots of people are like, I don't know what that is. And that's okay. We're going to talk through what that is. I have a list of what you do. So when you're not with me, if you're like, I don't know how to calculate the variance, if you go back to the list and you do exactly these steps, it's going to let you calculate the standard deviation. Obviously, that means you can also calculate the variance, because if you just skip the last step, because the last step is finally find the square root. If you stop at step 1, 2, 3, 4, 5, stop at step 5, you'll have the variance, and if you stop at step 6, you'll have the standard deviation. Question?
So sigma squared or S squared is variance. Variance is just whatever SD was squared.
If you're talking about the sample, because you're using S, yes. Or sigma, if you're using the sigma instead, you're talking about the population standard deviation. Yes, sigma squared would also be. Yep.
And what's the difference between what either of them presents? Because standard deviation is basically how far you are from the mean, but if you square it out, then
Right. The variance has really no physical meaning, but it's actually what it is that you're calculating in order to go get ourselves that standard deviation. Okay, she just said a bunch of words that probably sound really scary. Don't worry about that. We're going to get there. If you've already taken stats at some point in your life, you can start to have that conversation. But if you've never had stats before, none of those words made sense. That's okay. That's okay. We're going to get there. All right. Baby step our way in. The mean. How do I find the mean of a set of numbers? Beautiful. So if I want the mean of these sample scores down here, 92, 95, 85, 80, 75, and 50, we're going to add them all up. And there's 1, 2, 3, 4, 5, 6 of them. We would divide by 6. Is that okay? So let's do that. We're going to need the mean. So let's calculate the mean. I'm going to be lazy. We don't have to do it by hand. 92 plus 95 plus 85 plus 80 plus 75 plus 50. All right, I got 477. Did anybody else get 477? Good. All right. So my mean calculation, which in terms of a symbol, I don't know if you've done symbols yet, because this is a sample of scores. My mean is represented by an X with a bar over the top of it. Has she done that yet? Cool. And what we're doing is we added up those 6 numbers and we got 477, but I should probably write what we did just so that if you look back at your notes later, you know exactly what happened. We added them up. And then we divided by how many we had. So we have 477 in the top. We have 6 in the bottom. And that's going to come out to be approximately, well, not actually approximately, exactly 79.5. I'll get rid of my squiggle marks because it actually isn't approximately. I just thought it would be approximate, but it's actually equal to. Okay. All right. Here's the idea behind the standard deviation. Is 79.5 really far away from 92? No, but is it really close? No. If you had to give me like how approximately far away from it is, it's about 80, so it's about 12 away, right? And it's pretty close again to that one, but it's not super close. It's a little more, maybe more like 13, 14, 15 away, sure. But what about 50 to 79.5? It's way further away, right? So what we would say is that the variance is bigger. So when we say the variance, we're talking about how far away something is. The word that we use for the difference between the mean of all the values, the 79.5, and each individual value up here, the word we use for that is the deviation. So I'd say the deviation between here and here is a little more than 12. But I'd say the deviation from 50 to 79.5 is closer to 30. There's a way bigger deviation. When we have all the deviations and you add them all up, and then you take the square root of that, we call that the standard deviation. That's where the name came from. So deviations are just how far are each of the numbers away from the mean. So in our calculation, you'll see, I'm going to read through the list of things, and then you'll see where there's a difference that we have to pay attention to because I specifically said this is a sample of scores and not a population. So step 1 says, find the mean of the data. Cool, we did. Step 2 says, find the difference or the deviation between each of the scores and the mean. Okay, so to find the deviation, we're going to have to take 92 and subtract 79.5. And then we're going to have to take 95 and subtract 79.5. And then we're going to have to take 85 and subtract 79.5, like all the way through the list. So we're going to find the difference between each of the scores and the mean. And then we're going to square those things. And then we're going to add them all up. Then it says we're going to divide by the number of values. There's 1, 2, 3, 4, 5, 6 of them. If we're talking about the population, or we're going to divide by n minus 1 if it's a sample. In this case, I made it really clear it's a sample by like capitalizing the word and all of that. So instead of dividing by 6, we're going to divide by 5. We're going to do n minus 1. So we're going to do 6 minus 1. Okay. And then finally, we're going to take the square root of that variance, and it's going to give us the standard deviation. So you got the game plan down? Ready to see what we're doing? All right. Standard deviation. If it's for a sample, the symbol that we use for that is S. If it's for the population, we use sigma. And it's a different sigma than when we were doing our summation notation. You're going to use that cute sigma. But we're not doing that on this one. We're doing S on this one. Okay. So the way this calculation is going to go, we're going to have a big old square root sign. And I'm going to take the difference between each of the data points and the mean. And then I'm going to square them. And then I'm going to add them up. So don't be scared by what I'm doing. I'm going to take the first data point, which is 92. I'm putting it inside parentheses. I'm going to subtract the 79.5. I'm going to end the parentheses and I'm going to square it. Okay. And then I'm going to put a plus sign. And now I'm going to take the second data value, which is 95. And we're going to subtract the mean again, which is the 79.5. And I'm going to end the parentheses and I'm going to square it. And then I'm going to take the third data value, which is 85. And I'm going to subtract the 79.5. And I'm going to end the parentheses and square it. And I feel like I'm probably going to like run out of space. So I'm going to try and write even smaller. So as it becomes ridiculously small, forgive me. Then I'm going to add my next data value is 80 minus 79.5. We're going to end that. We're going to square it plus. Then we're going to do 75 minus 79.5. We're going to end that and square it. Ooh, this is going to be very hard for me to fit this into the end. Can I do it? I don't know. I don't believe in myself. 50 minus 79.5. It's not going to work, guys. I'm going to grab my other edge of paper here and fall off the side of my paper because it's just not going to work. Hopefully you saved more room than I did. All right, 50 minus 79.5. We're going to end that parentheses and square it. Don't laugh too hard. You're like, Jen, that's terrible. Yes, it is. It's terrible. Okay, so to recap what we did, we took all of these numbers and we subtracted 79.5 from each of them. And then we squared what we got. Now, what I'm going to do is draw a giant division bar under the entire thing. And we're going to divide by n minus 1 because this is a sample. Our n was 6 because we had 6 of these data values. And why do we subtract 1 from it? That's a really good question. It just works out if we do that, and it doesn't work out if we don't do that. That's a terrible answer, right? Statistics does a lot of that, where they're like, ooh, if you actually get like, they'll work out for you why it actually is the n minus 1, and the giant formula takes like 4 sheets of paper, and at the end you have no idea what just happened, and so you're like, it just works out better if you subtract 1, and people are like, okay, I'd rather have that answer because it's a terrible reason. But ultimately, it just doesn't work. If we leave it in as an n, the answer ends up being better if we don't. Okay, so now we obviously have to be able to do some math here, but not terrible math. It's more like making sure you don't make a mistake in your calculator math, right? It's not awful math. It's just like, ugh. Okay, so what we're doing now, at the end, we're going to take a square root. But in the meantime, what I'm doing is I'm going to take 92 minus 79.5, and then I'm going to square that number. 92 minus 79.5. I got 12.5, and I need to square that number. I get 156.25. Okay, then I'm going to do the 95 minus 79.5. I got 15.5, and then I'm going to square that number. I get 240.25. Then I'm going to do the 85 minus 79.5. I got 5.5. I'm going to square that number, and I get 30.25. Okay, now we're going to do the 80 minus 79.5. You could probably do that one in your head, but you don't have to. 80 minus 79.5 is 0.5. And then when you square that number, you're going to get 0.25. Okay, 75 minus 79.5, you might get scared. That's going to give you a negative number. But when we square a negative number and we've got parentheses around the thing, it's going to be a negative times a negative, and it's always going to pop out a positive number. So even when the number on the inside, when you do the deviation, is negative, when we square it, it comes out to be positive. And that's part of why we do this. We want all of the deviations to be positive, so we do that squaring to make that happen. So 75 minus 79.5 is negative 4.5. But then when I square negative 4.5, we get positive 20.25. Okay. And then last one, we got to do 50 minus 79.5. This one's also going to come out to be negative. So we get negative 29.5. And then we're going to square that. And we get positive 870.25. And then we're going to add all those numbers up and divide by 5. So I got 1,317.5 in the top. And I'm going to divide that number by 5 now. And I got 263.5. Since I've already fallen off the paper, I might as well keep falling off the paper. So I have the square root of 263.5. If I stop right here and I don't take the square root of this, what have I found? You found the variance. So if someone said, hey, what's the variance? Don't do this last square rooting. And you'll say the variance is 263.5. But since we said that we were going to solve for the standard deviation, we now want to hit our square root button. And when I hit that square root button, we get 16.23. This one I can use a squiggle on because it's not exactly equal to. I'll say 16.23. Okay, so I got to the end of that, and a lot of people are going to go, OMG, this is what statistics is? Oh, I don't want to have to do this. Here's the good news. They want you to see how to do this. They want you to know that that's what you would have to do. And if push came to shove on a test, if they gave you 6 numbers and they wanted you to go find the standard deviation, if you had a formula sheet that reminded you of what the formula was, could you do it? And I'm not saying because she's saying no calculators. So let's say you don't get a calculator on this. Could you have written this part and then left it just like that? This was the annoying part where we had to actually go through and do the calculator part, right? But without the calculator, if she just wanted you to set up how to do it, you just have to know that you had to take each of those data points and subtract the mean from it, and then put parentheses around it and square it, and then divide by n minus 1. And that's really what the formula sheet's going to remind you of. It's going to say, hey, that's the formula. And when she asks you how to do a standard deviation, she's just asking you, could you plug it in? Because in the real world, as a statistician, ain't nobody calculating a standard deviation like that. They're going to just put the data into R or SPSS or whatever statistical program that they're using, and they're going to put standard deviation and then hit enter, and it's going to spit out the number. You're not actually going to do this calculation. So then people are like, why do we have to do this? And go, they want you to know where it came from. Because otherwise, if you just get the number 16.23 popping out, you don't actually know what went into the process behind it. The process behind it was we took each of the deviations. And remember, the deviation is just how close or how far is that thing from the mean. So when I tell you that 16.23 is the standard deviation, and we go back to the very first step where we were looking at our data values, and I said, hey, like about how far away was that 92 from the 79.5? And you guys were like, it's about 12 away. But then when we looked at this one and we were like, it's about 30 away. If you took the average of all of those deviations, does it seem believable that that average would come out to be about 16.23? Because we got some 12s and we got some bigger numbers than that, but when we add them all up and divide, that 16.23 is kind of like the average of how far away you are from all of the numbers. So this one wasn't 16.23 away, it was about 12 away. And this one was about 30 away, but these ones were closer to like 12 away. So when we put all of them together and we add them up and we divide, we got 16.23. So it's giving us an approximate of how far of all the numbers are away from the mean. Not the median, the mean, sorry, I said the wrong word. That's what standard deviation is. Is that okay? It's weird. It's okay if you're like, that's weird, Jen. Yes, it's absolutely weird. Because the really good question was, but Jen, what does that variance mean? And the answer is nothing. The variance doesn't mean anything, which is why we don't usually like to give the variance. We normally give the standard deviation, because this number at least has some sort of physical, like, oh, well, all of these were about 16 away from that average number if we took them all and we averaged them together. That's all that's supposed to mean. Okay. Why do you care? Yes. Are there equations that will use the variance as one of the variables? In statistics in general, yes. I'm trying to think about in stat 13. In stat 13, you will absolutely see the standard deviation pop up a lot as one of the variables. Later when we get to, if we get to, they don't usually make it to the place where you would see it pop up as one of the variables again. They have something called like ANOVA, and it's a different statistical technique where the variance would usually pop up, but we don't usually make it that far in stats 13. It's sometimes put on the syllabus as like a maybe kind of sort of, they put question marks all around it. They hardly ever make it that far. But yeah, the thing to remember about the variance is just, if you take the square root of it, you got the standard deviation. That's really the, like when it comes up and people are like, what does the variance mean? The variance, people usually explain by saying it's the square of the standard deviation, is literally how people explain it. So normally we take it back to standard deviation because that has some sort of physical meaning, whereas the variance doesn't really. Why are we calculating the variance though? Because otherwise, which I'm assuming she probably did in class, if you take all of the deviations and you don't square them and you add up all the deviations, they always add up to 0. And then that's not helpful. So then she says, well, what we'll do is we'll square those deviations. And once we've squared them, we're in the land of variance. And then when we take the standard deviation, the square rooting of all of those squares is the thing that takes it back to something that kind of has a little bit of physical meaning. Have you talked about z-scores yet? We did talk about z-scores. Cool. All right. Then we're ready for the next handout. Z-scores and normal distributions are a big one. Game plan on copying out. I always do this kind of funky. Well, that direction. And that direction. And that this direction. All right. All right. All of this looks really weird at the beginning. So if right now you're still like, there's too many variables and I'm freaking out, I totally understand that. We just added another letter and we're like Z's now. Why are we talking about Z's? We want to be able to talk about how weird is a number. So if I'm going around the room again and I'm saying, we had a test and let's go with out of 100 again. So I'm going to say, you got a 90, and 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 you got a 95, and you got a 90, and you got a 90, and you got a 95, and you got a 90, and 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 I got a 10. We want to be able to talk about how unusual is my 10. It's pretty unusual, right? Okay. One thing that we want to be able to do is use standard deviations to help us come up with how do we assign grades. Do you know what grades are supposed to mean? They've been lying to you for a good long time. As an instructor, I find this very frustrating because at UC Davis, you're all used to being straight A students. So actual grades blow your guys' minds. Especially when people say, I really hope they're going to curve this class. And I go, here's why. Let me talk about something. You've seen this lovely distribution before. Your instructor's probably, oh, I gave it a long tail. I didn't mean to give it a tail. It was supposed to be roughly symmetric. There we go. That's better. A normal distribution-ish. If I take more of that tail off. Okay. Imagine Jen could draw something symmetric. A normal distribution is supposed to help us kind of figure out where should most of the scores be. So when I give a test, right down the middle is supposed to be the C grade. C is supposed to mean average. Now, you're all a bunch of really good students, so C is like soul crushing, right? And you're like, no, C is not good. No. That has evolved over the years. C's actually used to be perfectly acceptable grades, and people did not freak out about them because C was supposed to mean average. It was supposed to mean what most people got. And what I mean by most people is, see, that's the highest point of the distribution there. When we have distributions like this is where most of the data is. And then over here is supposed to be highly unusual. And over here is supposed to be highly unusual. When we're backwards this direction, these are supposed to be your F's, right? And then when you're over this direction, these are supposed to be your A's, highly unusual grades. And then the most usual grade is supposed to be a C. So how do we determine what's a B and what's a D? That's where the standard deviation comes in. So when we say standard deviation, we're saying how far from the mean are we? Our average is supposed to be the mean value. And so if you're one standard deviation away from the mean value, so if I go one standard deviation this direction, so I'll go from here to here, is one standard deviation. And I'll use the population sigma for the standard deviation. One standard deviation away that direction is supposed to be where your B values go. And then if you go another standard deviation in this direction, that's supposed to be where your A values go. So when you have a whole other one standard deviation, I didn't really mark that very well. Let's see if I can make this look a little bit cleaner. So you come over one standard deviation this direction, then that's where your A's are supposed to begin. Okay. And if you go backwards one standard deviation, that's where your D values are supposed to go. And if you go backwards another standard deviation, that's where your F values are supposed to go. So when you're at your middle value right here, that's your average. Okay. When you add one standard deviation to your average, that's supposed to be your B value. When you add two standard deviations to your average, that's supposed to be where your A's start. If you go backwards the other direction from your average, if you go backwards one standard deviation, that's where your D's are supposed to go. And if you go backwards two standard deviations, that's where your F's are supposed to go. Being one standard deviation away from things is pretty normal. Being two standard deviations away from things is pretty not normal. And so that's what this graph means with the percentages in it. If we're talking about a normal distribution, if we're right at the mean, so here's your C values again, this positive one and this negative one are telling you one standard deviation in the positive direction and one standard deviation away in the negative direction. From the mean to one standard deviation away in the positive direction, 34% of your data is supposed to be there. And then if you're at the mean and you go backwards one standard deviation, 34% of your data is supposed to be there. So for all the students in a class who get between one standard deviation below the mean and one standard deviation above the mean, so this would be your D and this would be your B, 68% of students in the class are supposed to get between the D and the B score. So most of the students, 68% of your students are supposed to be getting a grade in that range. So students who are getting a B all the way up to 2 standard deviations, so right where the 2 starts, that's where your A's are supposed to start. So this is telling you what percentage of your students are supposed to be getting a B. 13.5% of your students are supposed to get a B. And then this little tail here is telling you what percent of your students are supposed to get an A. If we take this number and we add this number, that'd be all your A's. If we just go from here to 3 standard deviations out, this would be like your normal A's, 2.35%. And then these would be like your A pluses, 0.15%. Super unusual to be 3 standard deviations away from the mean, like unheard of. So little, it's not even a whole percent. 0.15% of data is 3 standard deviations away from the mean. And it's symmetric. So if we come backwards, these are supposed to be your F's. There should only be about 2.5%, 2.35% of your grades being F's. Add on that part, that'd be like your super F's. Right? Now, if you know that, and you're in a class, and you get a C, you're like, oh, you did not do bad on a thing if you got a C in the class. Most people got that grade. That's where most of the data is. Falling between a D and a B is actually really good. And getting an A is supposed to be highly unusual. But that's if we're using a regular curve. Most curves people know from high school aren't real curves. Because if they were, here's the problem. I went around the room and I was like, you got a 90, and you got a 90, and you got a 95, and you got a 90, and you got a 90, and you got a 90. Well, guess what? If we add those all up and we divide by the number of people in the room, your average is supposed to be the C. If everyone in the room got a 90, it doesn't matter that I added you all up and I divided by the number of people. The average grade then is a C, and it's a 90. So a true curve would mean everybody who got a 90 on that test got a C. And then anybody who got the 95 now, they're the people who are going to get the better grade. So in a true curve situation, if people do really well on the test, then a 90 could become a C. And so when people say, I hope this class is curved, we're always like, what you actually hope is that it's only curved if it benefits you, right? Because a true curve could end up lowering grades. If everybody in the class got 100%, a real curve would make that a C. Everyone would have a C, which is nuts. No professor does that. I don't know any professor who, if everyone got 100%, they give them a C, but technically that's how it should work. So when we're talking about a true curve, they're talking about these percentages here. So in class, when we're talking about z-scores, that comes from this formula right here. Those z-scores are the numbers that are down here when I said we're one standard deviation away in the positive direction. This is a z-score of 1. And if we go one standard deviation away in the negative direction, that's a z-score of -1. If I go 2 standard deviations in positive direction, that's a z-score of 2. And this is a z-score of 3. Z-score of 3 is crazy unusual. We don't get z-scores of 3 very often because there's only 0.15% of data should be that. A z-score of 2 is also pretty unusual, only 2.35% up, and adding that on if we want to include that to say above a 2. 2.5% of data is going to be a z-score bigger than 2. So 2 is pretty unusual as well. But a z-score of 1, not unusual. 35% of the data would be right around here. Okay. And if you go backwards, a z-score of -1, a z-score of -2, and a z-score of -3 are mirror images of what's happening over here. So z-scores tell us how unusual the data is. Okay. So I'm going to write that off to the side over here. They tell us how unusual our data is. And I'll say data value is because we're usually talking about a particular value. So the other side of the paper has some problems where we actually are going to use this formula here. To use this formula, we got to know what these symbols mean on this side of the page. This down here, that's the sigma. Sigma is the population standard deviation. Okay. On this side, we've got the mu. That's the U with the long tail on it. It's called a mu. The mu is the population what? Average or mean. Yep, population mean. And then that X, that's just the data value that they gave you. So I'm just going to say given value that we're trying to figure out how unusual it is. So we turn things from X's into Z's. So when they're using this formula, the thing they're going to give you is some X, and they're going to say, hey, what Z-score would that be? So you'll take the X, you'll subtract the mean, and you'll divide by the standard deviation, and it's going to pop out a Z-score. And if your Z-score is like 1.3, I'm going to say not that unusual. If your Z-score is 2, I'm going to go pretty unusual. If your Z-score is 3, I'm going to go, oh, hecka unusual. Or other direction, if your Z-score is -2, I'm going to go pretty unusual. And if your Z-score is -3, I'm going to go hecka unusual. Z-scores around 1, not so unusual. So we got some problems. First one says, the average IQ of students in one calculus class is 110 with a standard deviation of 5. Okay. The average IQ of students in a second calculus class is 106 with a standard deviation of 4. Jorge has an IQ of 112. In which class is he ranked higher according to IQ? IQ is a dumb measure of things, but this was just something I pulled out of a book, so don't worry too much about it. But what we want to do, we got 2 classes. So I'm going to use a little sub 1 and a sub 2 to say class 1 or class 2. So if I want to figure out Z-score number 1 for Jorge,
we're gonna take his score. That's the X value. His score was 112. We're gonna subtract the mean for class 1. The mean for class 1 was 110. And we're going to divide by the standard deviation for class 1, which they said was 5. Okay, I'm not going to finish that calculation just yet. I'm just going to leave that there. That's what we would do. Then we would move on. I'm going to do the z-score for class number 2 now. You're going to take Jorge's score, that's 112. We're going to subtract off the mean for class number 2. The mean for class 2 is 106. And we're going to divide by the standard deviation for class 2. That one's 4. Okay. So now I'm going to actually go get those z-scores. This one is 2 over 5, which would be 4/10. I just did some magic there without a calculator. What? Yes.
So in this problem, we're assuming that the one calculus class is a population, like each one is a population?
Yeah. Good question. Otherwise, we can't do this problem. Yep. This one we have 6 over 4, which is 3 over 2, which is 1.5. So, how unusual are his scores? Being 0.4 away from 0 is our starting place. Not very unusual at all. 1.5, not crazy unusual, but it's getting pretty close to that 2 that is unusual. So he would be more unusual in class number 2. His score would be more unusual in class number 2. So where it says, in which class is he ranked higher? You would say he's ranked higher in class number 2. A particularly interesting problem, but it's a good way just to start to figure out how we're supposed to plug this stuff in. I like the second question better. And it kind of talks about more of the magic of how a z-score works. Z-scores are supposed to let you make comparisons between things that you wouldn't normally be able to make comparisons of. So this says, the average score on an English final exam was an 85. Whoa, people did good in that class. The average score was like a B, solid B, with a standard deviation of 5. So let's think about that for a second. If that's the average, that's the C. Isn't that crazy? That's the average. So that's really the C if the instructor decided to do a real curve. So when people say, I want them to curve this class, you go, hold on. Not always, because if this instructor curved this class, the people who got 85s all got a C because that's the average score. Okay? If that's the C, what score would the B be? If the standard deviation is 5. 90. A 90 would be a B. And so in order for you to get an A, what would you have to get? A 95, because A's are 2 standard deviations away from the mean. So if that's the mean, 1 standard deviation away would be 90, 2 standard deviations away would be 95. You got to get a 95 to get an A in that class if they actually did a real curve. So real curves sometimes are not what we want. Okay, but that's not the point of this problem. That's okay. This was an English test. The second thing says the average score on a statistics final exam was 110. So obviously it was out of more than 100 points. So maybe it was a 150 point test. I don't know. With a standard deviation of 8. If you earn an 80 on the English exam and 100 on the statistics exam, in which class did you actually get the more impressive score? Z-scores let us actually have this conversation, because otherwise, how do you talk about the difference between an English class and a statistics class when they didn't even use the same scales for the test? Like, maybe the English final is only out of 90, who knows? And maybe the statistics test is out of 125, who knows? We don't know. But if you calculate these things into Z-scores, you can actually make a comparison as to whether or not they did better in the stats class or in the English class, like compared to the other students in the class. So what I'm gonna do is I'm gonna write Z and I'm gonna put a capital E after it for the English class. Z of E. You could put 1 if you want, but I'm gonna use E since that lets me know it's for English. I need to put down the score that you actually got on the English test. We got an 80. And then I need to subtract the average score that the class got. They got an 85. And we always divide by the standard deviation that the class got. That was a 5. All right, I'm going to leave that there for a second. Then I'm going to do a Z with a capital S below it for the statistics class. We got to put down the score we got on the statistics exam. We got 100 on the statistics exam. But the average was 110. And then we got to divide by the standard deviation, which was 8. Okay. So this one, I get -5 in the top divided by 5. That gives me a Z-score of -1. So a Z-score of -1 means that you scored 1 standard deviation below the average on your English exam. So that technically should be the D, although that's really mean because you got an 80. So hopefully your instructor's not really going to do that to you. Let's see how we did in statistics then. So we got -10 in the top divided by 8. -10 divided by 8 is going to give us -1.25. This one, you actually scored even further below the average than you did in the English class. So you actually got a better score than in your English class than you did in the statistics class. Even though you got 100 on that statistics test and you got an 80 on the English test, you actually did better in the English class. Last one. The average age of accountants at one firm is 26, with a standard deviation of 6 years. The average salary of accountants there is $31,000. This is terrible. So I'm really hoping that they are in a state where they don't make that much money, because in California, that's a terrible salary for an accountant. With a standard deviation of $4,000. If a new accountant, so they just hire a new accountant, is 31 years old and earns $35,000, is her age or is her salary more unusual for the firm? So I'm going to do a Z for the age by putting a capital A, and I'm going to do a Z with an S for the salary. The age part, the age of this new accountant is 31. We got to subtract off the average age of these accountants. That's 26. And then divide by the standard deviation of 6 years. For the salary, this accountant's making $35,000. The average accountant is making $31,000. And we got to divide by the standard deviation, which is 4,000. Okay. So we get 31 minus 26 is going to give us 5.6 for this top one. I'm going to get it as a decimal for us. 5 divided by 6 is 0.83 approximately.
35,000 minus 31,000 is gonna give us 4,000 on the top. And we had 4,000 in the bottom as well, so I can do that one without my calculator. I got a 1.
So in terms of age or salary, how is the new employee more unusual by age or more unusual by salary?
By salary?
More unusual by salary, because the Z-score is higher. So that's 0.83. This one's a +1. So they're one standard deviation higher than everybody else in terms of salary, but they're not quite one standard deviation higher in terms of age. So the salary is more unusual. Good job. All right. You did excellent today. There was a lot of different formulas and things. I'm gonna go ahead and stop recording.